As you might have noticed in lecture 24, when we're dealing with finite limits of rational functions, we talked about the limit as x approaches a of some f of x, and we said that if this is equal to some l, we usually say that the limit of this particular function here is approaching that value L as x approaches a, and we wrote that, we said that actually this simply means that f of x is approaching L as x approaches a, right? And we also said that this also means the same thing as that, so this on this side also implies that. And we said that if x is equal to a, and we plug in that value a here, we get an undefined. We don't really care what is happening at x is equal to a, because we're only concerned about the neighborhood or the points we can pick closer to a and say what is the value that function is actually evaluated to. And we said that this value here is actually the limiting value of this function f of x as x approaches a. That's how you read this whole thing. The limiting value of this function f of x is L as x approaches a. That's how you read it. But technically, what this thing simply means is saying that can you pick a value close to a on the right and also on the left of a, and then so close that the calculator and the computer cannot pick the difference, and then you plug it in this function here. What is that value that you are actually getting? That's actually the meaning of this whole thing. Pick a value so close to a, plug it in the function. What is actually that value that you are getting at, right? Today, let me just give you just an example of what we're talking about. Suppose we said that find the limit as x approaches 3 of x squared minus 9 divided by x minus 3. And we wanted to find what this actually means. Is just saying that pick a value so close to 3. I'm going to say my x is going to be 3, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I have a 1 at the end. And also this one is the value that is on the right of 3, and then also pick the value on the left of 3 and say this is going to be 2.999999999. So I have 9 zeros here. Here I have 10 nines. So, and we want to find out what is this value that we are getting if I have to plug this value and that value. What is that value that I'm approaching? So if you grab your calculator and then you plug in these values there, what are you actually getting? So I'm gonna start with 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I place a 1. I square it up, I subtract a 9, and then I divide by 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I place a 1, and then I subtract 3 in it, which is this 3. So this x is the value that is so close to 3 that I actually pick. The value that I'm actually getting here is a 6. So this one, the limit. Now I'm going to try and put this value here. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I square it up. And then I subtract a 9. I divide here by 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I subtract a 3. So what am I actually getting here? I'm also getting a 6. So the limit of this, or the limiting value of this particular function, is 6 as x approaching 3. So you can actually do that because that's the meaning of a limit. Pick values that are close to 3, or you can go our route. You know our route, our normal route here. What we said that I plug in a 3, I know that this is going to be a 9. 9 minus 9 is a 0. I plug in another 3 here. I subtract that, and then I get a 0 over 0. If I get a 0 over 0, I factorize this numerator. I cancel out the common factor, and then I'm left with x plus 3. And then I plug in this 3, I will get a 6. So that was the meaning behind the limit, or how to find a limit. Now, today I want us to talk more about one-sided limits and their definition, what they really mean, and how to actually solve them. Let me pause this before I make this video long. Yeah, I've just cleaned it up. Now, let me look into this. Now, we talked about this and we said that this is a limiting value. And now, I want us to talk about the limit as x approaches a of f of x, and we're gonna say this is still equal to L. And I also want us to talk about open some space, the limit as x approaches a of f of x is equal to some L. But now, what I want us to actually think about is this. The limiting value now, I want to pick a point so close to a. I want the limiting value of f of x, right, as x approaches a, but on the right. You get what I mean? So what I actually wanted to do here, I wanted to say that I wanted to pick a point so close to a, but on the right. So the same thing we're doing here, because we picked 2 points. One was 3 comma something, which was on the right of 3, and the other one was 2 comma something, which was on the left of 3. Now I wanted to pick I'm just gonna start with this. Minus means that I am picking a point on the left of a, and then a plus here is meaning that I am only picking a point on the right of a. Right. So what does this mean, or how do we say this thing in words? We say that the left hand limit of f of x is L as x approaches a, from the left. So this one is a left hand limit of f of x, right? Is a left hand limit of f of x, and this is still the limiting value. So we can say that the limiting value of f of x as x is approaching a on the left is L. Or we can just say this thing, that the left hand limit of f of x is L as x approaches a from the left, right? Now, this simply means that other people like to say that the left hand limit of f of x as x approaches a is equal to L if we make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a and x less than a, something like that. But what is important here is that I am picking a point so close to a but on the left. A minus means just on the left of that point. And then this one here is just saying that the right hand limit of f of x is L as x approaches A from the right. That's what is important about this. So this one is saying I am going to pick a point so close to A but on the right, and then plug it here, and then that value that I will get, I will call it the right hand limit. Here I pick a point just on the left of A, and then I plug it here. The value that I'm getting, I will call it the left hand limit of f of x. Now, what is important about the left hand and the right hand limit is this. If the limit as x approaches A from both sides of f of x is equal to L, this simply means that the limit as x approaches A on the right of f of x is equal to L. And it also means that the limit as x approaches A on the left of f of x is L. So if you know the limit already exists and it is equal to some value L, you must know that by picking a point on the just on the left, the limit of that function is going to be L. And also on the right, plus means the right, and then on the left, minus means the left, of f of x is also L. And also, what that's supposed to mean, if you know the limit is equal to that of a function is equal to that, you must know these two limits exist by default. And if you know that this limit exists to be L and the left hand limit exists to be still L, then you must also know that this limit actually also exists. If this limit is a different value than the value of this limit, then this limit does not exist. Let me say this again. If the limit as x approaches A on the right of f of x, let's say it is equal to is not equal to the limit as x approaches A on the left of f of x, this simply means that the limit as x approaches A of f of x does not exist. So we want this limit and that limit to be equal for this limit to exist. Once these two limits are not equal, then this limit here we say does not exist. But if they are equal, then this limit will be equal to the value of this limit, which is equal to that. Let us take some examples to see how far can we actually go with this thing here. Okay, let me just look for examples here. This is my example here. Suppose I have my function here, and my function is characterized as I have, let me not make this too big. I'm going to say I have my p of x. So this function here is my p of x. Now, the question is, what are the values of the following limits if they exist? If they don't exist, explain why they actually don't exist. So I have this function here, which is given nicely as this these pieces of curves here. Now, the first one that I want us to look at is we want to find this limit here. I'm going to write here the limit as t approaches 2 on the left of p of t. What is the value to it? The limit as t approaches 2 on the right of p of t. What is the value to it? And the limit as t approaches just 2 of p of t. What is the value? And then we're going to look at the limit as t approaches, looking at this one here. Maybe I'm just going to write here. At this one, the limit as t approaches 6, I'm going to look at the left of p of t is equal to, and then I'm also going to look at the limit as t approaches 6 on the right of p of t, and then I'm going to conclude with that. Look at another example, maybe it's going to start making some sense. Now, let me grab a ruler here. Here we're saying we are going at t is equal to 2. Where is t is equal to 2? This is t is equal to 2. The minus is saying go to the left, on the left. So pick a point on the left. So if I were to pick a point just somewhere here on the left, right, what will be the output of the function just before 2? So if you look, when I'm going on the left of 2, I am going all the way, and then I'm going to hit this curve at this point. The value of the curve at this point is going to be 25. So here I am going to have a 25. So pick a point just on the left of 2, such that the calculator and the computer is not going to pick it up, but I've picked a point here. You can even see the difference is for you to see, but I'm supposed to pick a point just on the left of 2 such that the difference cannot be seen, and then I go to the function and see what is the point that I'm hitting there on the curve, and then that point I can see that is always gonna be 25 because this is a straight line. Now, once I am done with that, I am actually going to look for this one now. When t is equal to 2, this is 2. Now, the plus means on the right. So if I'm going on the right of 2, I'm supposed to be somewhere there. So if I'm going on the right of 2, what will be the output of this function just after 2? So I pick a point that is just on the right of 2 and go all the way. If you can see here, when I'm on the right of 2, I will end up hitting, of course, my line, just on the right of 2. My line is not that straight, but I will try. Just try. So if I pick a point just on the right of 2, you can see that I'm not going to touch this curve, and also there is nothing inside there. The point that I will end up just on the right of 2, the output will be there in this particular curve here just after 2, and this output here is going to be 26. So here I will have a 26. Let me write a 26 here. Now, if you look at this 26 and 25 are not equal. So the limit as t approaches 2 of this particular function, we say that it does not exist. So we want it does not exist. So this one and that one, they need to be equal for the limit to actually exist, because for it to exist, I need to approach 2 on both sides, on the left, on the left and on the right, but the value that I'm approaching must be the same. But because of this, we can see that actually the limit does not actually exist. Now, let's look now at this one here at t is equal to 6. First, we're going to go here, and then after that, I'm going to t is equal to 6, right? I can just place my line at t is equal to 6. So this is the output, right? Is the output at t is equal to 6. But I don't care what is happening at that point here. I wanted to first see if I were to pick a point just on the left of 6. So I would pick a point maybe somewhere here. So I would pick a point just on the left of 6. So if I go all the way up, what is that point on the function that I'm hitting? You can see that the point that I'm actually hitting is a 24. So here on the left, I have a 24. And then if I pick a point just on the right of 6, just on the right, such that the computer and the calculator cannot actually find out that value, the difference between this value that I'm picking and 6, what will be the output up there? So the output of that, or the value of the function at that point, just after 6, so it will be there. So what is that output? That output is still 24. So I have a 24 here. Because this 24 and this 24 are the same from the left of 6 and from the right of 6, then the limit as t approaches 6 of p of t is just going to be at 24. That's how easy this thing is. Also, another thing that we can actually try and talk about here is that I want you to take note of this. The limit at this point here, right, you can see that the limit here actually does not exist. But if I were to plug in 2, f of 2, you can see here I have a hole, but here is shaded, which means that f of 2 is actually that shaded value there. So it is supposed to be 26. So f of 2 is equal to 26. So even though this function is defined when when t is equal to 2 and it is equal to 26, the limit, we cannot say that the limit when t is equal to 2 is going to be 26, because these two limits are not the same. We want these two limits to be the same for the limit to exist at that particular point. But the function is defined. Even also here, because this part is shaded, so f of 3 is going to be that value there, which is 28. So we're going to have 28. And also at this point here, you can see that if we were to look at what is happening at this point, you will actually find out that the function is defined here, not there, because there is not shaded, it's only shaded here. So it is defined on the point where it is shaded. So the value of the function down there was going to be 24. So that's also something that I wanted to just mention here, so that we can see how we actually deal with functions of this kind here. Let's take another function here. And also, just for you to know, there is a jump here. There is a jump. That is why this limit does not exist, because there is that jump there. And when we are picking a value just on the right of 2, it just fall on this, which means that it's following the jump. Let's take another example here. Now, this example, we want to evaluate, we want to evaluate the limit as x approaches 0 of h of x, where h of x is equal to 0 if x is less than 0, and 1 if x is greater than or equal to 0. Usually, a function like this is usually used when someone is trying to mathematically model what a switch is actually doing. Those people who are doing electrical engineering, they know this function here, which was actually discovered by Olivier. What he was actually doing with this function, he was actually trying to say that when there is no current passing through, we're gonna say that x is less than 0. When there is a current flowing through, we're gonna say our x is greater than 0. And we want, when there is current, to say that there is a current by noting it by 1. And when there is no current, then we can just say that we have 0 current and place a 1 there. Now, we don't really care who came up with the function here, which was Olivier. I think it was a Scottish electrical engineer, I think so. But we don't really care much about who came up with this. What we care about is the limit of this particular function as x approaches a zero here. Now, if you wanted to deal with functions, especially step functions or piecewise functions, is always deal with this limit by actually evaluating one-sided limits or piecewise. Like first pick one value on the left and then the other value on the right and see if you are getting the same answer. Let's start by picking x, value x, on just the left of 0 here. This minus here is saying that we're going to pick a value on the left of h of x. Now, I'm going to place this. I'm going to have this one here. This one is going to 0, and then we have that. Okay. Now, if I were to pick a value just on the left of 0, a value that's just on the left of 0 is going to be negative. It doesn't matter whether it's so close or very far away, that x value is going to be negative if it's on the left of 0. So if it is negative, it's going to fall in this domain. So this is for negative value. So on the left of 0, the function that is characterizing a domain on the left of 0 is this 0 here. So this part here is going to be 0. Now, this is simply saying that if you had a Cartesian plane, these are the x-axis, these are the y-axis, at 0, at x is equal to 0, y is equal to 0, x is equal to 0 is along the y-axis, so y is equal to 0. So we have a function that is falling on the x-axis. So at any moment, I pick a value on the left, just on the left, is going to, its output is going to be 0. So this one here is going to be a 0. So the limit of this function here, of a 0 function, is going to be 0 right on the left. Now, if I look at the limit as x approaches 0 on the right of h of x, this is what is going to happen here. I have the limit as x approaches 0 on the right. Once I am on the right of 0, no matter how far am I on 0, just on the right of 0, I know that x is going to be positive on the right of 0. So it's going to fall under this domain here. X is going to fall under this domain, which means that my h of x now is going to be a 1. So I'm going to have a 1 here. So just on the right of 0, the function starts to go like this. So all the outputs, this is 1, all the outputs. So if I pick a value here and then I go all the way up to the function, the value that I will hit there is going to be a 1. So this limit here is going to be equal to 1. And if you look at this one here, because the limit, I'm just going to say, since the limit as x approaches 0 on the left of h of x is equal to 0, which is not equal to 1, which is just equal to the limit as x approaches 0 on the right of h of x. Therefore, the limit as x approaches 0 of h of x does not exist. So basically what is important, you need to find the limit on the left, and on the left of 0 you know that you are dealing with negative x values, and now if x is negative we know that our y is always going to be 0. That's what this means. And if y is actually negative, if y actually is equal to 0 for all the values that are in this interval here, which means that whenever I pick a value on the left of 0, I am always going to get an output of 0. And here, we are saying that we are looking on the right of 0, which means we are looking for positive values. If we are looking for positive values, we know that our y is equal to 1, which is this one there, and we have a straight line at 1. So this function is going to be 1. And if I'm going to pick any value just after 0, the output is going to be 1. So that's the output, which is 1. 0 and 1 are not the same. Therefore, the limit does not exist at 0. Let us try another example. Probably should be the last one. Last one? Okay. Let's see. The question would be, let me just change this now. What does the limit as x approaches 1 of the square root of x minus 1 evaluates to? Okay, so I want us to look at the solution of this thing here. Right. Always, if you noticed here, we looked into this either without, we could have plotted this, or could not plot it. We had something like this. So when x is less than 0, or when x is less than 0, starting at less than 0, the function was like this, so that you can see. At this point, it was not defined. We're going all the way like this. It was going this way. But when x was bigger than or equal to 0, we ended up having a nice function here starting at 0, and it was going all the way. It was going all the way like this, whereby we had a 1 here. So when we're picking a value here, the output was just there. And when we're picking a value here, the output was just there. So we had a 0 on the left, and on the right we had an output that is 1. So those two limits were not the same. But not always you can always plot like this. Sometimes you just have to analyze this form information as it is. Pick a value that is so close to 0, like negative 0,00000000000000001, and you plug it here, and then you see the output. And then because here is just 0, the output is always going to be 0. That's why we ended up here. And also here the output was always 1. That's why we ended up there. Sometimes you can plot, sometimes you cannot plot, but you need to be flexible and be able to deal with any situation that you have in your hands. Now, I want us to look into this, right? This function. Of course, we wanted to look at the function both on the left of 1 and also on the right of 1. Now, if let's say we want to plot this function, let's say we don't want to plot it first, because not every time we'll always be able to plot. Sometimes I just want to analyze what we're seeing based on the knowledge that we have. So first of all, I want us to look at the limit as x approaches 1 on the right of this function here. So I'm going to have x minus 1, right? And then I want to see what I'm going to get. And now I am also going to look at the limit as x approaches 1 on the left of this x minus 1. And then finally, I will look at the limit as x approaches 1 of this function here, x minus 1. Okay. Now, looking into this, this is saying pick a value so close to 1, such that the computer cannot pick the difference from the value you picked and x equal to 1. So here I am going to have a nice root, but the value that is so close to 1 is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I place a 1, and then I'm going to subtract a 1, and then let me explain here. And then we're going to hit an equal sign here. If I pick a value here that is so, oh, we're still here. A value that is so close to 1 but on the right of 1. As long as that value is on the right of 1, that value is going to be bigger than 1. That's what is nice about this. It's going to be bigger than 1. And which means that I am taking a value that is bigger than 1. I'm subtracting a 1. I'm always going to get a value that is positive, which means I will be able to take the square root. So as long as this value is on the right of 1 is bigger than 1, so I will be able to subtract 1 from it and still get a positive value. But now, because that value is so close to 1 such that the computer cannot pick, or the calculator cannot pick the difference. So basically what we are actually doing here, the calculator will just say, okay, because this value is bigger than 1, you can take the square root. But for me, because I can't deal with these things that you have the error is so small, what I'm going to do for you, I will just plug in a 1, and then 1 minus 1, you will end up having the square root of 0, which is just 0. I'm going to repeat it again here. When I'm picking a value that is on the right of 1, that value is going to be bigger than 1, which means I can subtract 1 from it and be left with something that is positive inside the root. If I have something positive inside the root, I can take the square root. So because I can take the square root here, which is fine, but the computer is saying, by having so many bunch of zeros, I can't deal with that. I'm just going to assume that is a 1. So I'm going to plug 1 for you and then subtract a 1, and then the value that you are actually approaching, or the limiting value, is going to be a 0. So that's what we're supposed to get here. Supposed to have as many zeros here. Yeah. So the more we add zeros, we end up having a 0 here. Of course, here you can see that 1 divided by 100,000, if I'm rounding it off, is still so close to 0. So it's just something of that kind. So the more I add zeros, the more I add in zeros, the more I'm actually closer to, because that value should be so close to 1, such that we get now a 0 there. Now let us look into this here. We're supposed to get a 0 there. Now let us look for this one here. I wanted to pick a value that is so close to 1, but on the left of 1. So if I actually pick a value on the left of 1, just on the left, so whatever that value is going to be less than 1. Because it is less than 1, you will end up with the negative value inside the square root. Right, let me repeat here. So if I pick a value close to 1 but on the left, that value here will always be less than 1. So I have something that is smaller, I'm subtracting something that is bigger, I will be left with a negative inside. Having a negative inside the square root, you end up getting an undefined, or a syntax error. Undefined. I'm saying undefined here. That's really not an undefined. You get an imaginary value. But here, while we are dealing with these limits, we want to get real numbers, not imaginary values. So I'm saying undefined because in this course we haven't yet talked about imaginary values and imaginary numbers. We're just gonna say it's undefined. Because undefined is not the same as 0, we say that this limit does not exist. Does not exist. So this limit does not exist. It only exists when this and that are the same. And if, let's say, here you are going to try a calculate and say, I want the leftover one is going to be 0, 9999999, and then you end up subtracting a 1 from it, it's gonna give you a maths error or a syntax error. So which means that this cannot happen. So in this case we have this and that. I hope this actually example gave you some insights. If let's say you just decided to draw this function, this is what will happen. But I wanted you to get both the understanding by just looking at the function and using the information that you know about the square roots, right? Now, if let's say you wanted to plot this function, you know that the square root always looks something like this. So you have y is equal to the square root of x, right? So when you have something like this, right, you will find out that actually we have something important here, right? Now look into this, take note of this. If you still don't know how to plot this thing here, we took it from this case that whenever I have x squared always look something like this. Y is equal to x squared always looked something like this. And then now when I'm interchanging x and y, I will end up having x is equal to y squared, and this is actually the inverse. So when I'm placing a mirror along the line here, y is equal to x, so this portion here which is going this way, it ends up being like that, and this portion which is getting away in the mirror, you end up getting something like this. So to plot this curve here, which is the same as y is equal to plus or minus the square root of x, you end up getting something nice like this, whereby this side is y is equal to minus square root of x, and this side is y is equal to square root x. So because this one is above the axis and the square root is always positive, the square root is always positive, but now we have this minus, so this one is always going to be below the x-axis. So to plot this, we usually go this way, but I know that you already know how to plot this function here. You don't need any help and any assistance on this. So if let's say we look into this, and now we want to actually plot y is equal to square root of x minus 1. Having a minus 1, we're actually minusing from this x here, which means that move this curve by 1 unit to the right. So it's going to move, this point is going to move here, this point is going to move by 1 unit, this point is going to move by 1 unit, this one is going to move by 1 unit. So you end up having a nice curve that is looking something like that. So this one is going to be y is equal to the square root of x minus 1. So we have something of this kind. So this is x is equal to 1. Now looking at the limit as x approaches 1 on the right, I pick a point just on the right of 1. So you can see that the point is going to hit the function, because the function is like, it's going to hit the function just, if I pick the point here, it's just gonna hit the function very close to 0. So that is why this one is going to be x minus 1 is going to be 0. Or alternatively, you can look into this. If I pick a point here, the output will be there. Now as I pick another point getting closer to 1 but still on the right, the function is going there, so it's gonna be approaching that point. And then I pick another point, the output will be there, so the function is going that way. And then as I pick another point, the function is going that way. So as I keep getting closer and closer to 1, the function is getting closer and closer to 0. So that is why the limit is like that. But when I pick a point on the left of 1, there is nothing to hit in this function on the left. That is why it is undefined, or there is nothing to hit on the left. So that is why we said that the limit as x approaches 1 on the left of the square root of x minus 1 is undefined, or someone can say it does not exist because there is nothing existing on the left, so it does not exist or undefined. Right, so we're getting an undefined, or here it does not exist because there's nothing on the left. So does not exist in 0 or undefined in 0, that's not a value. Hence we are saying that the limit as x approaches 1 of the square root of x minus 1 does not exist. Right, but the most common way to say this, we don't usually use this undefined here, we just say it does not exist. Does not exist. The reason is because there is nothing here, there is nothing existing here, so we usually use this one more often. Does not exist, so that this one does not exist also. So here because we're just analyzing, we end up saying undefined, but literally speaking we can say this limit does not exist. So that's what this thing is all about, or these nice examples on how to actually deal with these things. Right, now what I want us to talk about next would be, can you evaluate a limit as x approaches some value a of f of x, where when I am taking this value here a and I plug it here, I end up having f of a equal to a number which is not equal to 0 divided by 0. So in the numerator I get a number that is not equal to 0, but in the denominator I get a 0. How do we evaluate those actually limits if you get something like this? Remember we talked about a 0 over 0, and when we're dealing with that we said that what is actually important, you factorize. If you can't factorize, rationalize. If those two cannot be done, then you have two other methods that we haven't done. And we also talked about the limit as x approaches some value a of f of x. We said that this is equal to L if and only if the limit as x approaches a on the right of f of x is equal to L, and the limit as x approaches a on the left of f of x is equal to L. That's what we actually said. But in the next lecture, we will actually focus on how to evaluate these limits using this understanding of one-sided limits. Now, before I stop, I want us to talk about this symbol here, which is, if I were to write this like this, this one simply means that this is an implies symbol, which means that if this happens, then that happens. Right? Just like, if this happens, this one happens. But when I am actually having this one here, this one is if and only if, or just if and only if. The meaning of this is saying this implies that. So this arrow going this way, it says that this thing implies that thing. So if this one happens, it means that this one happens. Once you know the limit is equal to 5, it means the limit of this must also be equal to 5, and the limit of this must also be equal to 5. Now, and that implies this. So if the limit of this function as x approaches a is equal to 5, the limit on the right of this point is must be equal to 5, and the limit on the left at this point must be equal to 5. Now, having the arrow pointing that side, it simply means that if the limit is equal to 5 on the right and the limit is equal to 5 on the left, then the limit must also be equal to 5. This one, it means this implies that, and also this on this side also implies that. That's how we usually use this and the implies. So that will be all for now. Just try and see if you understood the concept, and then try and do as many problems and see if you can actually attempt, especially tutorial 6. You can try and keep checking it up. If you still can't solve, then follow this the next lecture on this lesson. I think it's going to be lecture 28. Then focus on that, and then if you still can't, then go to lecture 29, and then keep continuing like that, and then we'll be able now to finalize everything in lecture 20. I think in lecture 30 actually is going to summarize everything of how to actually deal with these limits. That will be all.